I will start with this. So first of all, I want to thank OpenACC organizer, in particular me to organize this, and for the invitation. It's great to have the opportunity, to share with all of you some of the efforts that we are doing at OpenL. So my name is Pedro Valero Lara, a computer scientist at OpenL. So I'm going to present one of the last efforts that we're doing on Kokkos. We call it KokkACC. Basically, it's a new Kokkos backend using OpenACC programming model. Okay, there you go. So the motivation of this work is programming productivity. What I mean by programming productivity is to create new programming models that can help programmer, application developer, to use different kind of architectures, efficiently and get a good performance with relatively simple code or simple or easier to implement codes. So what we can see in this slide is 4 different architecture for 4 of the probably today most important supercomputer in the US. So although we can see that there are some similarities in terms of architecture, in terms of number of CPUs, number of GPUs, and interconnection between these. At the end of the day, each of these systems use, different programming or software stack or programming solutions. So, for instance, in Summit on Permuter, so if we want to use GPUs, we need to use CUDA. While in Frontier, we need to use a different programming model, HIP, or in Aurora, we need to use a different programming model. In this case, SQL One API. So at the end of the day, what we want to do is to provide a highly programming productivity solution to mitigate or minimize, the modification that are necessary to make in the code to have the different code or the same code of the same application up and running on different architectures. So in this slide, I like always to put some examples about the definition or examples about what I mean with when I talk about programming productivity, because programming productivity can mean many different things. In my case, when I speak about programming productivity, it's all about developing a descriptive or agnostic programming solutions. Here you can see some examples or some definitions about what it means, right? At the end of the day, what we want, what I think is necessary today, I would say that even it's going to be even more necessary in the future, is to have less complicated programs, programming models that are easy to use and can be deployed on multiple different kind of architecture, and but at the same time, getting a good performance. So at the end of the day, what we want to have is a more proactive, programming ecosystem than reactive. So in that direction, this is we have Kokkos, right? Kokkos is probably one of the most important examples about highly programming productivity solutions that we have today. So Kokkos is open source, so everybody can access to the Kokkos programming model, and not only can access to the model or the implementation of this model, but also can contribute to that, and also can access to many other materials about Kokkos. I mean, tutorials, documentation, mini apps, etc. It's an open source, as I was saying, it's an open source performance portable C++ template and metaprogramming solution. I'm going to explain what it means, what this means, in the next slides. So basically in Kokkos, we have a unified front end. It's a C++ front end. And we have multiple different implementation of that front end using different, programming models, or the most popular and important programming model today. So basically, we have different backends for the same front end. So different backends are, for instance, CUDA, different backend using, for instance, CUDA, HIP, OpenMP target, others. And now we have the OpenACC backend too. So the OpenACC backend is a little bit different to the rest of the backends in many sense. In some sense, unless I will explain what are these differences in the next slides. For instance, one important difference is like OpenACC as Kokkos is a architecture agnostic solution. So so everything can be implemented, having any detail about the architecture or the parallelization, for instance, the granularity or many other factors. Well, I will present some of these differences or some of these, qualities of OpenACC backend in the next slides. So, to have one Kokkos application or Kokkos code up and running of different backends, the programmer must specify which backend to use at compilation time. So this is this can be done in a very simple way, so that you only need to set or use the Kokkos device macro, as we can see here in this slide, right? So for instance, if you want to have the Kokkos code up and running on CUDA, because you want to use NVIDIA GPUs, you need to set this backend equal to CUDA. If you want to use the OpenACC backend, so you have to set these Kokkos macros equal to OpenACC, and so on. So something to know, important to know, is that Kokkos can only use one backend and then one device at a time. With OpenACC, this is not true. So in OpenACC provide, as I said before, right, OpenACC is a little bit different to other backends. So with OpenACC, you can use more than one kind of device, in a runtime, as we will see in the next slides. So if you want to know more about Kokkos, so you can feel free to access this link that we have at the bottom right of this slide. You will find not only, the implementation, you will not only able to download and install Kokkos, but also you will find other materials, tutorials, documentation as well. So if we go to the next slide, there you go. Yeah. So here in this slides, I want to introduce you very briefly the Kokkos programming model. So in Kokkos, we manage the memory and the computation separately. So we have Kokkos malloc and Kokkos views to allocate the memory. And then we have three major different data parallel constructs. These are parallel for, parallel reduce, and parallel scan. In this talk, I will focus more on parallel for and a little bit on parallel reduce. So I'm not going to go deeply into the details because you can, access to the Kokkos repository. You can access to, all the material that are, about Kokkos. But I just wanted to give you, a brief introduction for you to understand what is the main characteristic of Kokkos, right? But there are more things, in the Kokkos ecosystem that I think that I'm going to present here. Okay, so but this can be a good, first introduction, to the Kokkos ecosystem or programming model. So at the same time, there are other 3 different modes or APIs depending on the data that you want to compute. For instance, we have single range that is more focused on unidimensional arrays, or vectors. Then we have a multidimensional range mode or API that is more about, how to compute if you want to compute or make some operation computation on matrices or 3-dimensional domains, things like that. Also, we have something called hierarchical parallelism. This is more different to the previous 2 different modes. It's more about, for those that are familiar with OpenMP nested. So it's a kind of similar. It's to implement nested parallelism in Kokkos. And it provides, the syntax and the API to do this nesting, to do nesting, and then to have a little bit more control on the parallelism and potentially more performance. So Kokkos is all about the use of lambdas. So the lambdas are passed as argument, in this parallel construct, like parallel for or parallel use. At the bottom, we can see a very simple, relatively simple example code for Kokkos, where we are doing an AXPY operation plus level 1 operation. So first, we allocate the memory. Then we initialize the vector. So this memory is S and Y are 2 independent vectors. So first we call a parallel for to initialize, these vectors, and then after that we make a AXPY operation using the same parallel construct, right? So this is how Kokkos code looks like. And as I said, so Kokkos is a C++ front end with different backends. So it means that exactly the same code, the code that we see here, can be deployed on many different architectures. It can run on NVIDIA GPUs, AMD GPUs, Intel GPUs, CPUs. So without changing one line of code. The only thing that you need to change to have the same code about running on different backends or different devices. If I come back to the previous slide, so the only thing that you have to do is to set this Kokkos macro, right, to the corresponding backend that you want to use, right? That in most of the cases, the backend is very related to the device that you want to use. For example, NVIDIA is NVIDIA GPUs, or to use NVIDIA GPUs, you should use maybe the CUDA backend, although you can use, for instance, the OpenACC backend too. Yeah. In this slide, again, I don't want to go deeply into the details about the Kokkos API or the OpenACC implementation of the OpenACC backend of Kokkos, but because there are many information there. Also, you can access to the OpenACC backend implementation in the link that we have in this slide at the bottom right of this slide. But I want to give you some details. I want to highlight some important things about the OpenACC implementation of the Kokkos frontend. So Kokkos and OpenACC have many things in common. So both are, architecture agnostic solution. In many cases, even the same terms or the same methodology or idea behind, the different, operations or features are exactly the same in both solutions, in Kokkos and OpenACC. All this makes the implementation of the Kokkos front end using OpenACC extremely easy. So, for instance, here we can see, well, on the left, we see 3 different, very simple examples of Kokkos code to compute AXPY operation on vector using single range on the top, using multidimensional range in the middle. So we are computing AXPY operation on matrices instead of on vectors. And then at the bottom, we have the same operation, but instead of using multi-dimensional range API mode, Kokkos mode, we are using the hierarchical parallelism. And on the right, we have the implementation of that. So as you can see, the OpenACC implementation is extremely easy to do. So for instance, the implementation for the OpenACC implementation is just a question of adding one OpenACC decorator or OpenACC backend, sorry, OpenACC pragma. So maybe the only thing that make the OpenACC implementation a little bit different to what maybe everybody that have used OpenACC for the application is that we have to transfer the lambda or the functor, to make it run on the different devices. But the rest is exactly the same to the standard OpenACC. So for example, single range, we need to use just OpenACC, a very simple OpenACC pragma parallel for loop. While maybe in a multi-dimensional range, it's a little bit more complicated, but we only have to add the collapse, as you know, a keyword of the collapse word, in the as part of the pragma, and that's it. So it's extremely simple to implement. A little bit more complicated is the hierarchical parallelism. As I said before, hierarchical parallelism is about nesting. We can implement nested in this way, decorating the function that is going to be computed in a nested level by using worker. And on the top of that, we use, again, a very simple parallel for pragma, OpenACC pragma. So it's relatively straightforward. Also, other Kokkos features or Kokkos provide atomic operations as well. And well, this atomic operation, again, can be implemented in OpenACC in a very simple manner as well. So, the conclusion of this slide is that, okay, just because of these similarities between Kokkos and OpenACC, in terms of synthesis, in terms of features provided, so the implementation is extremely easy. In this slide, I'm focused on performance analysis, right? So we have used one node of the Summit supercomputer. Summit, I think today is the top number 5 fastest supercomputer today, if I'm not wrong. So for the performance evaluation, we have used different backends. So we have focused on using one NVIDIA. Well, there is an error here. I have just realized that it's a V, not C, V100. It's a Volta NVIDIA GPU. And we have used all the backends, CUDA backend that we can use for NVIDIA GPUs today in Kokkos. They are the OpenMP target backend, the CUDA backend, and then the OpenACC backend. So we have used a relatively simple mini benchmark. In fact, the graph on the top in that section corresponds to the code that we have seen in the previous slide. So basically, AXPY operation on vector and matrices using a single range. On the left, using a multidimensional range API in the middle, and using a hierarchical parallelism on the right. On the bottom, we have exactly the same, but instead of computing AXPY operation, we are computing a dot product. So we have to use parallel reduce instead of parallel for this operation. So as we can see, the OpenACC backend is, in general, is much faster than the OpenMP target backend, or provide much faster or better performance than the OpenMP target. And with respect to the CUDA backend, is either the OpenACC performance is either faster or better or competitive with CUDA. So one can get surprised, about this number, how OpenACC can provide better performance than CUDA, right? When OpenACC is a higher level solution and CUDA is a low level solution. This is because of the particularities of Kokkos. I have some more results, or low level results in the next slide, but I want to highlight one thing here. So the point is that, as I said at the beginning, Kokkos is all about lambdas, right? And lambdas are passed as argument. So in other words, so when you implement things like parallel for construct of Kokkos or parallel reduce construct of Kokkos on the different backends, the developer or developers don't have any idea about what they are going to compute. So we don't know which kind of operation we are going to compute. Things like if it's going to be a compute-bound operation, it's going to be a memory-bound operation. So we are not idea. We don't know how many registers we are going to use, how much of the memory we are going to need. And at the end of the day, what is the best configuration for that computation, right? Oh, it's extremely difficult to know. So for things like CUDA that are, programming models or relatively low-level programming models, where you have fully control, on the device that you want to use, and you can make many different settings. In OpenACC, you don't have control at all. So you rely on a compiler and runtime to decide those details for you. So in this particular case, where we are not idea about what kind of operation we have to compute, things like OpenACC can provide are a very good solution, or can provide, something more, than other solutions, right? And at the end of the day, no, the OpenACC backend is not much simpler to implement than maybe other backends, but at the same time can provide a competitive performance, or even in some cases, much better performance. So here is a very particular example where relatively much simpler codes can provide much better performance than other much more complicated codes. And that's, I think, that is a good progress to have highly programming productivity solutions. On the right, we can see some other examples using some ECP scale computing project mini-apps, but the conclusion are the same. So we see that OpenACC can provide or provides much better performance than OpenMP target backend, and either competitive or better performance than the CUDA backend. So just to give you an idea about which kind of operation are these, so miniFE is a computational fluid dynamics. Well, it's a finite element method simulator. LULESH is a thing that is about particle simulation, if I'm not wrong. And LAMMPS is something similar to LULESH in the sense too. So there are three different operations or three different applications completely different each other, where the conclusions are basically the same. Okay. In this slide, basically, I'm analyzing the performance, but at a lower level. So I'm analyzing the performance not only in terms of time, but in terms of number of instructions, also the block size, number of wraps used, and in particular, the bandwidth that we are able to get in the different, hierarchy of memory of the GPUs. So once again, we evaluate this while running this test using 3 different backends: CUDA, OpenACC, and OpenMP target. So the number that are highlighted using different colors, red for CUDA, blue for OpenACC, red for OpenMP, are those numbers where provide the best numbers, right, for that specific test case and metric that is evaluated, right? So as we can see in most of the cases, the best performance is provided by the OpenACC backend. So as I say, right, in this particular case for Kokkos, where the computation that we have to make, or we have to compute, or the kind of operation, or the operation that we have to compute, is something that we don't know when we implement the different backends or the different implementation for the front end, from the Kokkos front end. Things like OpenACC is the tool that can provide an added value, and not only simplifying the implementation of these backends, but at the same time provided a very good performance. This is something that I think that many people don't know very well about OpenACC. So OpenACC is not only for GPUs or NVIDIA GPUs. It can run on CPUs as well. And in fact, not only you can run OpenACC code on CPUs, but you can get very good performance as well. So just to have a code, or OpenACC code, up and running on CPU, the only thing that you need to do is to add a compilation, a flag in during the compilation. So as simple as that. So, and then you can use exactly the same code running on CPUs. Here, what we see is once again, very simple test cases: AXPY and DOT product, AXPY and DOT, the product on bottom. And I did the same test cases, or some of the test cases that I have presented in a previous slides, but on 2 different CPUs: Intel CPU with 20 cores and AMD CPU with 64 cores. What we can see is that, and then we see OpenMP, we see the time for OpenMP using the OpenMP backend and the time for the OpenACC backend. What we can see is that the OpenACC provides very competitive performance with respect to OpenMP on 2 different architectures. For parallel 4 on top, I'm doing AXPY on top, and also for parallel reduce on bottom. So this is something that OpenACC provides. OpenACC, the OpenACC backend of Kokkos is not only for NVIDIA GPUs. It can be also for other kind of GPUs using different compilers. But at the same time, also you can have the OpenACC backend of Kokkos running on CPU very well. Once again, this is one more thing that OpenACC helps for to have highly programming productivity solution. In this case, in Kokkos. Not only that, right? So as I show you, in the previous slide, okay, we can have OpenACC up and running on CPUs and GPUs, but we can do even go further, and then we can compile, the same OpenACC code, or in this case, the same Kokkos code on 2 devices. So we can have the same Kokkos code up and running on CPU and GPU at the same time. And then at runtime, we can decide which device to use, according to the or depending on the complexity of the application and the characteristic of the hardware. When I say characteristic of the hardware, I mean the capacity of the CPU, the capacity of the GPU, and how these are connected to each other. So this is something else, as you know, one more time, something else that the OpenACC backend can provide, you know, towards, you know, improving the programming productivity for Kokkos codes. That it can be more complicated or even not possible in other backends. To make, you know, to delegate, you know, the selection of the device to Kokkos, we implemented a new function that we call a Kokkos set device. And in that function, we pass as argument a tuning factor. A tuning factor can be the number of operations, or can be other factors important for the you know, for the application.
There's a question, Pedro.
Yeah, I see here a question from Damian. I know Damian.
Yes.
Yeah, so yeah, that's a very good question, Damian. Productivity can be measured in many different ways, as you know very well. Productivity. So it can be measured in the sense like, okay, how simple is the code? How many number of lines of code do you need to implement, you know, the different, you know, feature of Kokkos? Using, you know, in this case, OpenACC versus maybe using CUDA or HIP. And productivity can be also measured in the way, okay, in this case, in one single or using one single backend, how many different, you know, devices can you target or can you deploy on, right? So in that sense, you know, OpenACC backend can be deployed on many different, you know, backends. So in these two different levels of different, you know, duration, I think that the productivity is better, right? In OpenACC, is good in OpenACC. I see here a different question as well, maybe, Izumi.
Yeah, the question was, he made a comment, so Damien made a comment that says it does not change anything for Kokkos user code.
Yeah, it's totally correct, and I totally agree with Damian when he said that at the end of the day, this doesn't change much for Kokkos user, but it changed a lot for Kokkos developer or for how Kokkos is implemented. So here, you know, in this work, I'm not focused on the front end. In fact, I'm not, in this slide, you can see that we implemented something called Kokkos set device, right? And we will see what can we do there, right? With this single, you know, function. But I'm more focused on development of backend, of how can we improve programming productivity, not at level of Kokkos user, but at level of Kokkos developers, and how to make the implementation of Kokkos more productive, you know, in that sense. And yeah, I totally agree with Daniel when he said that. Yeah. So if there are no more questions, let me continue.
There's one more question. So I have a question that came in on a Slack channel that says, is it possible to use this with an OpenACC code and a Kokkos-based solver and try Linux?
So with this Linux. Okay, I'm not familiar with Linux. Unfortunately, well, Damian responded that. I think that Damian is
not yet. Okay.
Is involved on that, so it's very good to have Damian attending this. He's helping me with this, so that's great, Damian. I will have to invite you to something, after the webinar. So yeah, absolutely. Yeah, so it looks like not yet, but maybe in future.
Perfect. Yeah. Thank you.
Thank you, Damian, for your help. And well, so with this KokkACC device, as I was saying, we have to passage argument a tuning factor that can be many different things. As I will show you in the next slide. So here we can delegate to Kokkos the selection of the device that we want to use, right? So how that affect to the implementation? Well, it doesn't affect a lot. So for instance, for single range, Kokkos API, you don't have to change one line of code. So the only thing that is going to change is how, this Pragma ACC parallel 4 is going to be implemented at the end of the day, right? If at the end we have this code running on CPU, we will use a coarser granularity, right? While if we run this code on CPU, we will use a fine-grained granularity, right? But this is completely transparent to Kokkos user, as Damian mentioned. So it's completely transparent to that to Kokkos user, and it's also not only transparent to Kokkos user, but it's also transparent to, in this case, the OpenACC backend developers, which is also, appreciated when you are a developer. But what about for instance, the other implementation, for instance, multidimensional range? The things can change a little bit here, right? So in this sense, depending on, and there are implementation detail that can be done better, but just for clarity, I have simplified as much as possible the implementation to make everybody to understand what I want to say here, right? So the point is that for multidimensional range policy, in this case, let's imagine that we have to make some computation of matrices. So we have to change the implementation depending on the target. I mean, if and this is because on CPU we have to access to the memory in a completely different way that we access to the memory if we run the code on GPU, because the granularity that we are going to exploit is different. And so just to make everything working well and fast, so we have to swap, the order of this for loop. This is one way to do it. There are other ways to do it, maybe better than this, but then, for these cases, we have to be careful in the way that, the memory is accessed. But look at this, right? So it's not very complicated to implement this, right? So in this case, just swapping the order of the for loops, or the nested for loop, we can have a very good implementation for CPUs in this case, and a good implementation for NVIDIA GPUs. Just adding a few lines, we are making Kokkos able to have good implementation for different devices in the same backend using OpenACC. Okay. If you want to access to what we call Kokkos, F means smart Kokkos, because we delegate to Kokkos the selection of the device. So you can access to this repository or to this link here, and you will access to the implementation of this. Here, once again, some performance analysis, in this case using Kokkos, on two different heterogeneous devices. Equinox with one Intel CPU and one NVIDIA GPU, and Zenith with one AMD GPU and one AMD CPU and one NVIDIA GPU. So once again, here we run simple test cases, AXPY and DOT product on single range, using vector and matrices. On two different heterogeneous systems. So what we see here is that, the red line corresponds to the OpenACC backend running on GPU only. The dark blue line corresponds to the OpenACC backend of Kokkos running on GPU only. And then the light blue is this Kokkos, right idea. And we can see, depending on the complexity or the number of operations or the computational cost of the operations or applications, so it's not very clear which is the best device to use. And then we see that in this case, Kokkos, sorry, there is an error here. It's not KokkACC, it's Kokkos. Sorry for that. So Kokkos is able, to make a good decision, right, about the device to use depending on the computational cost, right? So we see that the Kokkos is able to make a good transition, between using CPU and start using GPU, increasing the complexity of the problem. There are things that can be improved, for parallel reduce. Parallel reduce is a much more complicated, operation, to estimate the performance and to make the decision. But at the same time, I mean, it doesn't look very bad to me, So with Kokkos, once we are able to delegate the decision of the device to use to Kokkos. And this is what we can do right now, right? So depending on the computational cost of the operation and the characteristic of the hardware, we can make the decision for you about which device to use, either the CPU or the GPU. Here is the same. I'm extending, the performance analysis study by using a only relatively simple mini benchmark, but using application. So something that I forget to mention in the previous slide. So let me come back to the previous slide very quickly. So as a tuning factor here, we use the number of operations. In this benchmark or mini benchmark, we basically have one single, basically parallel 4, parallel reduce. So they are very simple, test cases. For real application or mini apps, the things change, right? So in application, in most of the cases, we don't have one single parallel 4 or parallel construct or a couple of parallel 4 parallel reduce constructs. We have more than that, right? And also in every parallel 4 or parallel reduce, we have to make different computations, right? So it's much more difficult to deal with, right? In terms of what are the tuning factors that we have to use. So here we have three different, once again, three different applications. So in LULESH, basically, LULESH is a set of extensive computations. So we have to make many different kind of relatively simple operation on 3D domains, a kind of extensive computation on 3D domains. So for LULESH, the most important factor is the size of the domain. In miniFE, is a final element, simulator for CFD. So basically, miniFE compute a conjugate gradient method for using sparse matrices. In the conjugate gradient method, the main bottleneck there is the computation of the matrix vector computation. So as I say, so we are using sparse matrices here. So the important factor here, the most important factor for this mini app is the number of non-zero elements. In Lattice-Boltzmann is a method for computational fluid dynamics simulation. In this case, it's a very memory-bound operation. So in this case, the most important factor is the number of operations. So we use different factors depending on which of these factors are more important for the different domains that we have used or different applications that we have used, and then we run Kokkos, right? And we can see here, we see in most of the cases, we see that Kokkos is able to make a very good transition between using CPU and GPU, depending on the computational cost, using this factor tuning on 3 different applications. In some cases, we see that it could be better. For instance, here, it could be a little better because we make the transition maybe later than it should be. It should be the transition should be done here, but it's done here. Also here, maybe once again, maybe the transition could be a little bit better. Oh no, here is, yeah, it could be better. So but overall, we see that Kokkos is able to make a good decision about the device selection, transparent device selection. And it's true that in some cases, in these boundaries between, the use of CPU is better on GPU or vice versa, we see that the transition could be better. But overall, I think that these are good numbers. And not only that, we delegate the decision about device selection to Kokkos, which makes the life of application developer much simpler in that sense. And,
Pedro,
yeah,
we have a number of questions.
Oh yeah.
So first question, do you allocate in unified memory? Does this consider data transfer?
That's a very good question. I don't allocate unified memory, and I'm not doing data transfer here, Damian. So at the very beginning, when we do the Kokkos set device, we set the device that we want to use. And depending on as I say, depending on the tuning factor, depending on the characteristic of the application, characteristic of the hardware, and then when the device is set, the device is not changed. So we are all the time using the same device. So we are not transferring any data. So what a heuristic? So there is other question, right?
Yes. So what heuristic do you use to decide whether to run on CPU or GPU?
Yeah, so there are many things there. So you can find information, you can find the details in the repository, but it's about the gigaflops, or the capacity of the CPU, the GPU, also the bandwidth about how these CPU, GPU are connected, and some other factor about the implementation. For instance, it's not the same. It's not the same to estimate. I mean, we cannot estimate the performance in the same way for parallel for than for parallel reduce. So there are some details there, but basically, the heuristic that we use is relatively simple. We are working on making the things better in that sense, and maybe use more sophisticated, heuristic. But right now, we are using the one that we are using are working really well, and less on the tests that we are using. So yeah, it's all about the hardware and the tuning factor, and then depending on these two things, we can estimate the time running the application on CPU and running the application on GPU, and then make the decision.
Perfect. Thank you.
Sure. Okay. No more question, right?
There was a comment. Response to your previous answer was, so not a per kernel decision, but at the app level.
Yeah, correct. Correct.
Perfect.
Correct. I mean, that is what I'm trying to explain, in these two last slides. Yeah.
Thank you.
Absolutely. So I will continue. So I think that it is one of the last slides. So this is just basically a summary about what I have been saying, along the talk. So I think that it's better to focus on descriptive or agnostic solution more than restrictive device-specific solution. Kokkos provide at the user level, provide a descriptive agnostic solution, and that's very good. And that's very important to increase the programming productivity, for HPC and scientific code. And that is for Damian is doing an extraordinary work on that direction. But at the same time, I think that we can exploit that also at implementation level as well, not only at the user level, but at an implementation level. And this is an example about how things like OpenACC can help, in that direction, yeah, well, I think that that's all right. I think that rely on compilers is better than rely on the decisions that CUDA developer had to take, that in some cases maybe are not the best, depending on the operation that had to be done or will be computed, by the lambdas. Something that the developer cannot know, when they are developing the backends, right? So yeah. So I think that is the conclusions, about how OpenACC can help in that direction, in particular for Kokkos, but maybe for other solutions too, right? And I'm going to go to the next slide. Well, conclusions. OpenACC provide competitive or even better performance than CUDA backend. In many cases, it's much better than OpenMP target backend today. So can work well, not only on GPUs, but also on CPUs, on Intel and AMD CPUs. Something that I forgot to mention when I was presenting this performance, for the OpenMP backend, I use the vendor compilers, Intel compiler and AMD Clan compiler for this comparison. We are trying to go further and enabling Kokkos with transparent device selection for heterogeneous systems. Here, some results of our initial effort in that direction. Some future and an ongoing effort that we have in mind for this is the support for multi-GPU. As you could see in my first slide, today most of the supercomputer, we find a relatively high number of GPUs, in all the supercomputers. I'm talking about nodes. In every node, we have a relatively high number of GPUs. So it's important to provide that support, and also distributed memory support, not only for single node, but also for different nodes. It doesn't mean that today we cannot run Kokkos on distributed memory. We can, but we need NPI, on top of Kokkos for that, or maybe other things, BIGAS or other things to do that. And I think that this is the last slide. Yes. So just some acknowledgement. I want to thank the KokkACC team. Here is a picture of some of the KokkACC teams, John, Joel, and Mark. This work was awarded as a best paper award in one of the supercomputing workshop last year. So we are very happy for that, and we want to thank, Veronica was one of the organizer, or the main organizer of that workshop. Veronica is in the photo, in the picture. And I want to thank the ProteaStone, the ACP ProteaStone project. We have used funding. That is the funding that we have used for this work. I want to thank Jeff Petter, which is not only one of the co-author of this work, but also is the head of this ACP project. So thank you so much, everybody, and KokkACC team, for this work, for this collaboration. And with this, I think that this is all